Good afternoon and welcome all to advanced features of the DecisionTools Suite version 7 that you may not have used yet. We're going to have a bit of fun today. I've got about an hour lined up of features that have been part of the product, sometimes introduced recently. Some of them have been around for a very long time. But my experience with our client base has shown that a lot of people don't fully explore the products, and there are plenty of options in here that do add value to the process or to whatever decision assessment or value add you're trying to achieve, but you're simply not aware of these things. So hopefully some of the ideas that we come up with in the next hour will help you add a little bit more perhaps sophistication, perhaps some more to the reporting, a little more to the accuracy or usefulness of your modeling. And so let us begin. I'll start today by looking at a few tips in at-risk. And the first one, we'll be looking at, pardon me, simply a blank spreadsheet. Let's talk about inputs. Now, when you run a simulation and you have multiple outputs, hopefully you're all aware of the various techniques available to you to generate overlay charts for your outputs. However, prior to even running a simulation, of course, you need to include your inputs. For some people, that process involves deciding between various distributions. But not everyone is aware that when you actually define your distributions in the first place, you can use this dialog to immediately compare different shapes to understand where they could indeed be different. So I'll choose a few distributions. I'll start with an inverse Gaussian function. Now perhaps some of you aren't as familiar with this function, so why not teach you a few little things. If I'd like to just remove this curve, I can hit the little X, and now I go back to the, something that's a bit more familiar, let's say the log normal, and we'll start here with this log normal distribution with standard parameters mu and sigma 10, 10. To overlay another shape on top of this, I can click the Add Overlay button, which is along the bottom of the window. Now this icon is the at-risk's universal chart overlay button. Wherever you see this, you can overlay something, and that will be context dependent. Here, I can add an overlay as a distribution chosen from my palette. So on top of the log normal, I will go and collect my inverse Gaussian function that I generated before, close my overlay dialog, and now I can see how these two different functions may look. If I change pardon me, my means to be the same, I can now see what a log normal 1010 might look like compared to a inverse Gaussian 1025. Let's expand my window here so I can also see the statistical comparisons between them. If I choose to, I can of course compare more than just two distributions simultaneously, and I'll get to that shortly. Just one more thing that wasn't on the agenda but that people might want to start considering. If you don't know what the mu and pardon me, lambda parameters for an inverse Gauss represent, perhaps you could define your distribution using a 3-point estimate instead. So I'll put my estimate at 10. I'll say the low 3 is okay for that, and I'll put a high at say 20. So now I'm comparing an inverse Gauss function that's being defined using alternate parameters to my log normal. Okay, so perhaps via two different methodologies, I have determined that these are reasonable parameters for a standard log normal, perhaps using historical data. And that these three parameters may be reasonable or have been produced via some sort of estimation methodology. And now I can compare what those two different choices would look like across their range. I would do so immediately by looking at the chart, moving my delimiters, and comparing especially their various tail probabilities. The straightforward statistics, the moments and percentiles can also be compared in the table on the right, but otherwise I would look at these two and determine which one best suits my actual needs. Let's throw a third distribution on top of those. I'll add an overlay now, and I will add, let's say, a PERT distribution. So I now have 3 overlays. I can extend my window to get results for all of these. Let's put the mode back to 10. So now I have a comparison visually across my 3 distributions. What I don't have currently is a comparison in the delimiters across those. Right-click the chart, select Graph Options, and I can now change the number of delimited curves from 2 to a larger value, say 3, and now I've compared all 3 charts simultaneously. If I add more charts, let's say I'll grab a uniform distribution, you can see that I still only have the 3 charts there, so how about I go a little bit over the top and put in, say, 10 delimited curves. So now any overlays that I do up to and including 10 different functions simultaneously, I will get information about their various percentiles in the delimiter section along the top. The most, I guess, important information will be the tail probabilities, these sections here. And because I'm building things that are right skewed, probably the tail that I'm highlighting over here now. This will be the key area. And so although I could do this in tabular form, it's also, of course, very simple to simply look at the chart and compare this right-hand side. Perhaps we could ask the question, what probability of exceeding 40 would I be comfortable with? About 2%, practically nothing, 0.5%, or 20%. Now with these options chosen, perhaps it is in fact the inverse Gaussian function that I'm most comfortable with. Well, it's simply a matter then of me clicking the delete curve for everything I don't want. I'm left with my inverse Gaussian function. I click OK, and that now is the one that goes into the spreadsheet. So I'll simply use that overlay option again, either just by myself as I did then, or as a way of describing perhaps to a workshop or room full of people who have different opinions on what the appropriate distributions and parameters should be. We can pull up that comparison chart and immediately talk live about the functions that are being discussed and see that, or pardon me, and see which one seems more appropriate for our particular circumstance. I'm going to put that file away now, and let's dive into some of our example spreadsheets. The next topic that we're going to look at are scatterplots. Okay, so to produce a scatterplot, I need to run a simulation. I'll just run a quick sim. Now, if I look at my simulation data, I can see that I obviously have MPV, I've got an output there, I've got my development costs, initial unit cost, demand, and so on. I have all of these variables, both my input random variables and then my output values. Scatterplots of those inputs and outputs, pardon me, can help give me an understanding of the relationship between the inputs and the output. It generally falls into the category of sensitivity analysis. So if I wish to get a scatter plot of my output, my MPV, and one of my inputs, I can right-click the output cell, go to results, and with our new version 7 right-click functionality, which is a bit easier to use now, there's a scatter plot option. So I click scatter plot. At risk asks what do you want to have a scatter plot with. So let's look at company share of demand. I click OK. And I get a scatter plot of MPV compared to company share of demand. I note that the correlation, the rank correlation, is around 0.2, so quite weak, and I can see that relationship in here. Now, just like basically all of the charts you'll create in this form using at-risk, this one is live. I can move the delimiters up and down to get information about different quadrants that are of interest. Perhaps say 1.5 million and a 70% market share. I can see that if my market share was below 70%, then in a ratio of 0.6 compared to 20.4, I can see my MPV would either be above or below 1.5 million. So it's just another visual way of understanding or analyzing your simulation results. I could also move my cursor to the middle of the chart, so to the intersection of the two delimiters, and move these around simultaneously, and the quadrant percentages update live. Okay, so I might look at company demand at 80% and the MPV at 1 million. And I can now see what the relative likelihoods are of being above and below in all four combinations of those particular scenarios. I can also create a scatter plot without having to, pardon me, or I should say in the opposite direction if you like. So I can simply select, let's grab unit cost. I can select the cells on the spreadsheet. So I've selected these two by pressing and holding the control key. Now when I right click and go to scatter plot, the cells have already been selected. So it immediately creates a scatter plot of those two variables, the input and the output. Further to that, I can actually have overlay scatter plots. So I'll select my MPV cell, then my initial unit cost and my initial unit price. Right click, scatter plot, and I get the overlay scatter. So I can see the negative relationship between unit cost and MPV as expected, and the positive relationship between unit price and MPV. And I can also see which one is stronger. Okay, I chose those variables because the initial unit cost and initial unit price are of a similar scale. If the scales were too different, then the scatter plots will be harder to see. But as you can see here, I can overlay a comparison of the two variables against the MPV. Now, there are other ways of getting those particular scatter plots, and then also other versions of them. If I use my right-click options to go to a tornado chart, let's say a correlation tornado. So this will rank my inputs according to the strength of the observed relationship between each input and each output value in the simulation data set. I get a tornado chart. Most, if not all of you, will be familiar with these charts. However, you may not know that if you click on one of the bars, drag and drop it off the window, you can also create a scatter plot. Okay, so I can see here the moderate strength relationship between initial demand and MPV. Okay, or the inconsequential, fairly inconsequential relationship between development costs and MPV. Very, very minor, almost insignificant negative correlation. All of the tornado charts, correlation and regression tornado charts, have this feature. The change in output statistic tornado has the same feature, but with an added extra. So when we rank the inputs by their effect on an output statistic, an assumption is made that we're going to divide our inputs into a certain number of scenarios, all of equal probability. So the standard is 10 scenarios. I did 5,000 iterations, so I have 10 scenarios, each of 500 values. And for each of those 500 values from low to high, I can calculate the mean of the output for those 500 input values, with all of my other variables, of course, taking whatever random values they took in that simulation. So nothing will change the scatter plot of unit price to MPV, but if I create the scatter plot from this tornado, I get some extra information. And I'll zoom in here. So this should look familiar. This is the tornado that we created seconds ago. But now some, in this case, a total of 10% of the scatter plot has been color-coded. So on top of the dots representing the lowest 10% of initial unit price, blue dots have been laid over those red ones, blue crosses. This indicates that scenario for which the initial unit price is at its lowest 10% of values. The expected value of those blue dots, that is the number that we will find on the tornado chart. 426,700. Bring that out again. 426,700. So around this level, which by eye you can see is about right. Likewise, there are green circles covering the highest 10% of the initial unit price values. Between them, they have an expected value of 1288. So what that refers to is, of these green dots, the mean seems to be about 1.2, well, is calculated exactly at 1.2. So I now know how the width of the tornado bar is generated by looking at the scatter plot. So this scatter plot, even more than others, is not just useful, it also helps to explain how this tornado chart works. With a strong positive or strong negative relationship, the end scenarios will almost always be the ones coinciding with higher and lower, the highest and lowest values for the statistic of the output. But possibly, as I have in this case, there is such a weak relationship between development cost and the MPV, it just accidentally turned out that it wasn't the very highest values of development cost that coincided with the lowest values of the MPV. But that's not indicating some strange nonlinear relationship or non-increasing, non-decreasing relationship between development cost and MPV. It just is indicative, in this case, of the weakness of the relationship meant that randomly, any of the lowest scenarios for development cost may have been associated with the highest expected value of the MPV, and any of the higher scenarios for development cost may have been associated with the lower values, lowest mean for the MPV. Now those results all are derived from simulation results. What I'll also show you just quickly is if I grab a couple of variables and create a correlation matrix, here is another place where I can generate scatter plots, but a scatter plot that I'm going to predetermine, if you like, and that is in my correlation matrix. So here is a scatter plot between these two inputs, unit cost and unit price, and then a small scatter plot showing me the relationship as it currently stands at 0. If I click, drag and drop that chart off into open space, I get a bigger scatter plot. And then when I go back to my matrix, as I move my slider up and down, the small but also the larger scatter plot shows me what that relationship would look like. From perfect positive to 0 to perfect negative correlation in terms of the coefficient or correlation matrix method. Okay, so here's another way I can generate scatter plots. If I go through the same process with copulars, I will also be able to see what a scatter plot between these inputs will basically look like when I then do go ahead and run a simulation. But that's something that we would predetermine or predefine. Okay, I'll put that one away. I'll go and grab another simple model, and let's talk about the model window itself. Again, I know some of our users spend a lot of time in the model window. Some don't even know what the button does. Let's explore this now. The model window, sometimes referred to as the double down arrows for obvious reasons, is quite simply a list of all of the inputs, outputs, and correlation structures you've created in all of the workbooks in this Excel session. More on that point later, because that can become very important. But for now, what do I get a look at? I get to see very quickly how many inputs and outputs I have. I get to see what inputs and outputs I have. And if I click on them, you see that at risk navigates to that cell in the spreadsheet, wherever it is in the spreadsheet. Okay, so it's a useful way of not just finding out what exists in your model, but also literally going straight to anything that you found or that you would like to then look at. So perhaps my year on oil production distribution, if I just click OK, I will be there, or I can right click and edit the function directly. There's the function. I could make changes. What can I do in this dialog beyond just finding things? If I click in the function window, I get input properties about my input. Perhaps I would like to use a separate seed. Perhaps I'd like to lock it, collect, pick other options. I can pick these options from here. I can also change the name by clicking in the name window. Clicking here in the name window. If I'd just like to get a graph of the distribution, I could just double click then and produce this chart. So I've got some descriptive information to sort of help me out there. Something else that I can do is make some changes to my model as needed. Now let's say, for example, that the CapEx has now been determined. This doesn't need to be a distribution anymore, okay? Or I simply don't want it to be a distribution. Perhaps it was put in mistakenly, or indeed any of my other distributions that I have. I can choose any of these, but I will go to CapEx. I can simply click the delete button or right click and delete. It will remove the function entirely and replace it with a static number. I click yes and I click OK. So when I go to my CapEx, it's replaced it with the 1.2 million that was there before. Sorry, the static outcome. But it has removed the function perfectly. So when you go in there and you edit things yourself, you can potentially make mistakes with what's left over and so on, or remove part but not all of the function, or accidentally delete part of a cell content that you didn't mean to delete. Well, using the model window is a way of ensuring that precisely and only the at-risk functionality is what's being deleted. I can do the same for outputs. Now in this case, I'm very happy for that functionality because in a not especially useful way, all of these cells have been made outputs when possibly I only need the MPV. Okay, I probably don't need everything here to be an output. And if I check my model window, I can see that in fact I have 63 outputs. There's the price of oil range, price of gas range, OPEX, oil revenue, oil production, the net cash, maybe I'd like that. Okay, gas revenue, gas production. Let's say it's only the MPV I want. How will I remove these output functions so that I'm not simply wasting my computer's time and effort storing data for 62 unnecessary outputs? Well, I could potentially try to find each of them on the spreadsheet and remove them. So I go to 1, edit output, delete the range. Okay, so that one's gone. But now I've still got all of these other outputs. Well, I can do that sort of thing en masse in the model window. I can delete outputs one at a time, simply deleting, or I delete a whole bunch by clicking on one output, say pressing the Shift key, holding it, and just like highlighting multiple cells, I'll highlight the lot, hit the delete key, and delete those. Or I can select actual ranges of outputs, right-click, and delete. Or multiple ranges. So I've deleted all of those now. I get rid of the OPEX. So I could have done this all in one go. I'm just showing you how you might want to just eliminate certain outputs. But now I'm left with the MPV. Just the MPV, excellent. Click OK. All of those output functions are gone, except the one that I want, the MPV. If I go back to the model window, I see I only have one output now. Now this model doesn't have a correlation matrix in it yet, but I will grab one. Let's get oil and gas production. And I'll create a quick correlation matrix, 0.7. It's okay. Select the location, I'll put it over here. Great, so I've got a correlation matrix. Now when you use correlation matrices, quite a lot actually happens to your spreadsheet. Firstly, the functions that you have correlated now have risk format functions inside them. There is also a named range. I've just got the default name new matrix 1 here in your spreadsheet that represents the correlation as well. So simply deleting these cells here doesn't get rid of my correlation matrix. Instead, it produces errors because these inputs are still looking for that matrix. And at risk will also be expecting to be able to see this. Absolutely the easiest way to remove correlation matrices is in the model window. I can simply select it, delete the matrix, click OK. At risk perfectly removes the matrix from my spreadsheet and also the risk format functions from the cells. So for removing inputs and outputs, and especially correlation matrices, because there's a lot involved in a correlation matrix, the model window is a great place to go. Now, one very useful feature of the model window is an extension to the idea that it tells you how many inputs and outputs you've got. It also lets you know which books you have open, which spreadsheets or workbooks you have open that have at-risk functionality. If I now go and open another spreadsheet model, and I click the model window, I can notice that the number of inputs and outputs I've got has increased, but I can also see that I have a workbook, Oil Drilling Schedule 1, and another workbook, Oil Gas Forecast 1, both of which have at-risk functions in them. And I can navigate between the two workbooks by selecting different inputs or outputs in each model. Okay, so I can use my pardon me, model window to let me know exactly what I have open and where everything is across multiple workbooks. For those of you who look at pardon me, advanced simulation setting options, such as the use of a fixed initial seed, it will become very important for you to know whether or not you have other workbooks open or anything else that has an at-risk function in it, because that will impede your ability to get reproducible results. The last thing I'm going to look at with at-risk are some advanced analyses options. So the advanced analysis button is up in the tools section, and there are 3 tools in there. These are goal seek, stress analysis, and advanced sensitivity. Now, broadly speaking, I refer to all of these as being a type of sensitivity analysis, but each of them has a distinct purpose, and we'll quickly identify what those or what that purpose or those purposes might be now with a few simple examples. So if I go to the advanced analyses section of the example spreadsheets, I see that there are a couple of examples. They're all simple examples, but a couple of examples for the goal seek, stress analysis, and advanced sensitivity. What I'll do is I'll initially look at a very simple version of each and then a more complicated one. So let's look at goal seek. This is one of my favorite features because it enables us to do some quite sophisticated things, especially in an environment where perhaps we can't easily understand inputs in the model. Maybe we would struggle to parameterize them or produce, distributional assumptions and so on. Or maybe the value of a numeric parameter is difficult to estimate, if not impossible. What we can do instead is in a model, just like the regular Excel standard goal seek, I can find what value of a particular cell will generate some feature of another cell that I'm interested in. Now, unlike Excel's goal seek, where I would change a number to get a particular value for a function, this model is probabilistic. So my output has essentially an unlimited number of values. What I need to understand firstly is that it is not a particular value of the output that's of interest. It will be a characteristic of it, such as the expected value or the standard deviation or some percentile. There will be a characteristic of the output that I am interested in, expected return and so on. In this particular model, our two variables, revenue and cost, have a standard deviation factor. So they have a base standard deviation and then the potential to change that standard deviation by changing this factor here. I know it's a pretty obscure sort of example, but it's supposed to be simple to show you how the feature works. What we would like to do, the model's already been built in here, so I'll just go to goal seek. What I'd like to do is to set the profit cell's standard deviation, amongst other things, but I'll use the standard deviation, to the value of 9,000. So I would like the volatility in my profit to be 9,000. And I want to do that by changing this factor. In other words, what level of volatility do my revenue and cost distributions need to change by to achieve a standard deviation for my profit of 9,000? And in terms of accuracy, I'm willing for it to be within plus or minus 1%. And I will also put in limits on what that factor can be. The tighter the limits, and still of course being logical, then the quicker the algorithm will work. So I think that the factor will be somewhere between 0.5 and 1. Okay. I'll just exit this, so I'll turn off the charts. All right, let's analyze and see what comes up. Now in the information bar along the bottom, it worked too quickly, but along the bottom it tracked its attempt to achieve a standard deviation of $9,000 for the profit. It turns out that the factor needs to be 0.68. So if the volatility in revenue and cost were reduced by a factor of 0.68, I would get my profit standard deviation down to $9,000 as I would like it to. Now this probably isn't a specific application that any of you are working on. Obviously, the model's too simple. But the idea is transferable to anyone working in spreadsheet modeling. There is a value on the spreadsheet that I would like to change or find a critical amount for to determine some characteristic of my output. An example that I've seen is looking at a long-term commodity price and what value that needs to drop to make the expected return of an investment 0. So if the expected return gets down to 0, it's not feasible. We might decide sooner than that, but it's not feasible. So what does that long-term commodity value need to be? This is, like I said, a simple example looking at standard deviation, but anything that we may not be able to model with a lot of confidence, we can find out what are some key values for that. Perhaps we're looking at the probability of a risk event occurring. What does the likelihood of that risk event need to get up to before the P95 of my total project cost exceeds some critical level? Just as an example, and there are an infinite number of such examples that we could work on. A more specific example of goal seek is here, where we're looking at a model with puts. So now we're suddenly getting to something a lot more complex. So the model is small, but we've got Black-Scholes equations, we've got the exercise price of the put. Now I won't get into the technicalities of it, but in this case, at-risk goal seek is being asked to get the expected value of the portfolio return to 8.6% by changing the exercise price of the put. So very simply, what value is the exercise price, or what value does it need to be to generate this expected return? Simulations are run because it is a stochastic model, of course. And I see that I can get very close, so 8.585% by having the exercise price set to $77.96. So it was 90 before. Now at this level, $77.96, I will have an expected return of 8.6%, or near enough to 8.6%. So just a specific example, but trying to show you again the idea of being able to change something in my model and generate a particular outcome. Stress analysis. Now, stress testing means different things to different people. The stress testing that at-risk does, generally speaking, again, I've got a super simple model here, is instead of allowing your input distributions to sample across their entire allowable range, we will restrict the sampling to a stressed scenario. In the example model that's here, we are going to monitor our profit cell and look at the stress, which is that the revenue distribution is in its worst 5% of outcomes, and at the same time the cost distribution is in its worst 5% of outcomes. If I go to edit these, I can see I could stress lower, or like low values, high values, or put in a custom range. I can determine what low, high, or custom means. I can also, pardon me, stress different aspects of the model. Now, if I just analyze this, what's going to happen? We can see that 2 simulations will be run, each with 5,000 iterations. What's actually going to happen here? Well, the stress analysis, for it to be meaningful, needs to compare itself to the base case. So in the base case, my model will remain as is. In the stressed scenario, revenue will be very bad and cost will be very bad as well. Now I can stress each of these individually. So let's just look at what happens when revenue is bad, and let's just look at what happens when cost is bad. Or I can stress all of the inputs in one go. So I'll quickly do both of those options, stress each input in its own simulation. And now I have 3 simulations. So base case, stressed revenue, and stressed cost. Now that the simulation has been run, I've got some results comparing baseline to what revenue or cost look like. I have some quick comparisons here of how the expected value changes, standard deviation changes, P5 reduced, P95 reduced, and so on. And I have some summary statistics. But I also have all 3 of those simulations at the same time. I've used the Show All Sims option here to create an overlay. And just a little reminder of the delimiters rule. I've got 3 curves here, so I'll change the number of delimiters to 3, delimited curves to 3. And so now I have statistical information on all 3 of those scenarios. And this I could use to compare, for example, relatively, how bad is it when cost is bad compared to how bad it is when revenues are bad. So my baseline is in red. Graph options here, let's just make the 2 scenarios, lines instead. So I have my base case, and I see that when cost is bad, I have the green scenario, which is bad, pretty bad, but it's not as bad as when revenue is in its worst 5%. And I could see the various statistics or graphically see that when revenue is bad, I have a much greater downside. Okay, so that was stressing the variables individually. And the other stress option is to vary them one at a time, all at the same time. So now I only have 2 simulations of the base case versus everything being stressed. So you can see that when I stress both at the same time, I get a much worse outcome than either individually, like quite obviously. I can put that away. Let's go back to my model. And show both. And I see that I have my base case and then my stressed distribution way down here. So that's both things being stressed. So as I said, you may have a different definition of stress testing, but if your stressing is about particularly bad outcomes or regions or neighborhoods, then the stress test option is for you. So these are values of the input distribution. And lastly, but not least, for our at-risk section today, we'll be looking at the advanced sensitivities, the actual advanced sensitivity option. Pardon me. So in this particular case, I have a model that also is in the example spreadsheets. New product 2, so you can have a look at that model separately. Now, instead of just running a simulation and getting the regular sensitivity analyses, I can use advanced sensitivity. Now, what does advanced sensitivity do? You pick a particular cell, so I've got an output here. You pick various inputs, In this case, I've picked things like development cost. Let's just edit that. And what I'm going to do is choose a range of values to test for each of these and run a simulation for that. So I will hold, say, the pardon me, CapEx costs here to be very low, run a simulation with all of the other variables sampling randomly, and see what my results are, and then test different values along that range. I could also do the same just for a cell. So I'll show you the example here is the discount rate. So the discount rate is 8% as typed into the model, but I could change it across specific values or do a percentage plus or down, or choose a table of values. In this case, we're going from 6%, so 2% lower, up to 10%, 2% higher, in 3 steps. So in other words, 2% lower, on 8 exactly, and 2% higher. Now what's going to be done is, one at a time, each of these variables will be converted, if you like, into this sensitivity function where it's simply going to choose those particular values that we've suggested and simulate for each of them. For each of those simulations, I will be mainly interested in a particular statistic. The one that's currently being selected here is the expected value, and I'll just stick with that. But I could also generate, pardon me, or track a percentile, or even the volatility and so on. Various results that are possible, I'll just take the ones that are here already. In this particular case, I don't need charts. There would be 56 simulations needed. So all of the inputs are each going to be tested at different values and a simulation be run for each. So a particular variable, such as the CapEx here, development cost, will be held to its P1, and everything else gets randomly sampled, and I'll generate results, including the expected value of the MPV. Then the CapEx will change to another value, say the P5, and another one, P10. And for each of these options that I've specified, a simulation will be run. On the left, you can see the progress window showing that we're moving quite rapidly through the options. 56 is quite a large number of simulations to run. That's why the number's only 1,000. You probably don't need to run as big a sensitivity model. There's probably fewer things that you're most interested in. But as you can see, it still doesn't take very long to run 56,000 iterations. Now, what do I have with my results? I have a spider chart comparing or showing for each of my variables. In this case, this is the top 6. As these distributions were held to their P1 or 5 or 25 or 50 and so on all the way up to 99, what was the value of the mean of the MPV? So if I compare a steep line here, such as initial unit price, the dark green, I see that there was quite a big change in the mean, whereas the dark blue line, development cost, had a very minimal change in the mean profit. Here I'm comparing, oh, pardon me, looking at how much as a percentage change from its base value did the inputs vary and how the mean varied. And here I'm comparing the variables themselves in a particular type of sensitivity into how they are influencing the expected value of the profit. So this is a slightly different but related result to the actual tornado chart looking at change in output mean. This is being generated differently, but another way of asking the question can produce this tornado and this ranking of variables and their importance. And in the summary, all of the data is there in case you're interested in checking out some specific stats. And also, all 56 simulations, 1, 2, 3, 4, 5, all the way, 56 simulations worth of data is being stored simultaneously for you that you can then analyze in many ways, or in many ways, well, as many ways as you know how to analyze data without risk for any other information that you would like. Okay, so I'm going to leave at risk there. And we're going to look at PrecisionTree next. As always, at risk is our flagship product. It's the really big product. It's the piece of software, the tool that has far and away the most options. So it also has the most options that you probably haven't used before. The next products we're going to look at will all be quicker to go through because they're all smaller in size, so there are fewer things that you probably haven't encountered. So let's go straight to PrecisionTree, and we'll look at a couple of options. The first option I'll look at, again, I'll start with a blank spreadsheet, is the Append Tree option. Now, building a tree is simple. Click Decision Tree, get it started. Hit a node, change what it is. Let's say it's a decision. So let's change my calculations to automatic. There we go. After that decision is 2 possible chance outcomes. After all of those chance outcomes, now might be a set of 3 decisions. So you can see pretty easily, as my tree gets bigger, even if I use copy and paste, it can take a while to build. So that's only 3 levels. And what if after each of these, I had a chance outcome with 3 different options? You can see it's taking a long time. Is there a quicker way to build a big tree? Absolutely. We'll start with a single node, and then I'll use the Append Tree option. Now what Append Tree enables me to do is let's start with a decision. This is just decision 1. It's got 2 branches, as we have above. After that comes a chance node. It had 2 options as well. After that chance was a second layer of decisions though, but this time there were 3 decisions. And after that was a chance node, also with 3 choices. Now obviously I would actually build in what some useful names are, but I'm just trying to reproduce the structure down below. So I simply name each layer, click OK, and PrecisionTree has built the whole tree. I'll zoom out so we can see it. Up the top, this is what I started to build myself. With a few clicks in the Append Tree option, P-Tree built this much larger tree for me very, very quickly. Even if I needed to make a couple of changes to the structure here, maybe remove the 3rd option here, or add another option, a 4th option here, and so on, this is often going to be quicker than trying to build the tree one step at a time. So if you can or do have a decision tree structure where it's relatively symmetric, in terms of after each chance or decision, there are pretty similar, at least numbers or types of options, this method will build you a big tree very, very quickly. So that's the Append Tree option. I'll put that away. Now we'll take a very quick look at sensitivity analysis. I have a simple bidding model here. This is where we are deciding whether or not to bid for a project. Now, we need to decide whether we bid or not, and then decide whether we will bid low, mid, or high. Now, it turns out that just using the base numbers that we have, we should bid, and we should bid a moderate amount because that has the best expected return. But that particular path, that policy suggestion, is based on the parameter values that we included in our model. What if we are not certain about what these values will be? For example, what is the cost to us of the project? Maybe what's the bid cost? Maybe what's the probability of other people bidding, and so forth. So where we have uncertainty, we need to vary things. We vary things in PrecisionTree using sensitivity analysis. Now I'll start with a one-way sensitivity. And what we do is identify cells in our spreadsheet that should change. In this case, the cost of the project to us. We can identify how we would like to vary it. In this case, just from 140 to 160,000, we might change that. Maybe let's put a bit more downside on that. We'll go, oh, that's all right, I'll leave it as is, just so you get the same results if you do it yourself. And then we also have the cost of the bid and a range of possibilities there. So a one-way sensitivity will produce results, tornadoes, spider charts, that indicate relatively which of the inputs that I've identified have the greatest effect on the value of the tree. I've also asked here for a strategy region chart, which will let me know what is the sensitivity. Actually, I'll grab a sensitivity graph as well. I'll get all those results. What is the sensitivity of the optimal decision to changes in these variables? So in a decision tree, it's not just the value of the tree that could change, it's also the optimal path. So let's click OK and get some results. So I can see here that as the actual cost of the project to us increases, there's a reduction in the expected value of the tree. But there are also some bends in the model here, or in the curve, I should say. Likewise, as the cost of bid goes up, the expected value of the tree goes down as well. Now, what's causing that? Well, for the project cost, as the cost goes up, the value of the tree, if I bid, this blue line, goes down. And it gets to a point at about 155,000 where it's actually it's more worthwhile to not attempt to bid because the expected return is now negative. So I have a crossover point here which indicates a change in optimal decision. This path is originally optimal. Now this path becomes optimal. Likewise for the cost of the bid itself. Once it goes much over 10,000, it's too expensive and we're better off not bidding at all. And as a comparison of those two things, I can see that the project cost is more important in some way than the bidding cost. And I see a spider chart comparing those options as well. That was changing one of those two variables at a time. I can also change two at a time with a two-way sensitivity. So it's the same variables changing in the same way, but this time I'm going to change them both. And here are my results. I have a 3D chart where I've changed the cost of the project, the bidding cost, and the expected value of the overall tree. This chart kind of looks cool, this 3D chart, but it's easier to view from directly above, and that's a strategy region. So I have these purple triangles for the do not bid option and blue diamonds for the bid option. And you can see like a border here. All of these combinations of these two variables indicate where do not bid is the optimal choice. Bidding is the optimal choice below that diagonal. So what that tells me is that the values that I've put in, 150,000 and 7.5, which sit right here, I'll get my highlighter, which sits right here, according to the tree, the best decision at the moment is to go ahead and bid. However, we can see that a very small change in either or both of the cost of the contract or the cost of the bidding would indicate to us that we shouldn't bid. So in fact, I have a very low level of confidence in the decision to go ahead and bid. Perhaps we should look for something else. I'm just now acknowledging how much exposure I do have. And it's very easy for me to, in hindsight, wish I hadn't bid it in the first place. So that's two-way sensitivity, obviously involving only two variables at a time. One-way sensitivity can involve multiple variables. So we could also include things like probability of other bidders and so forth. So you can have as many in a one way as you like. Now that decision to bid was based on expected values. And by default, and just generally, most people use the expected value option for their decision making. Well, at least if you like, from the start. But what we can also do is utilize a method called utility, which enables us to include risk aversion in the actual calculation in the tree. I have a drug development example here. So it's an R&D program for a pharmaceutical company. There are various options. They've got a new drug that they could start to do some testing on. Should we do that ourselves, get someone else to do it, or just sell the idea now? If we do the further testing and it's successful, should we then manufacture it ourselves or sell the idea off then? Well, based on expected returns, we should get someone else to run the first phase of the project. If it's unsuccessful, well, too bad, we'll lose a bit of money. If it's successful, we should manufacture it ourselves, and we might make a heap of money, or we could potentially lose a lot of money. So there is perhaps, with this big downside here, a concern about there being too much downside. Now, go to, I managed to close the example file. There are two ways of approaching this, and actually I'll flip it around. I'll look at forcing first. What I could do is look at, say, the risk profiles of all three of my key decisions, whether to sell the product straight away, get someone else to model it, to do the testing program, or do the testing program myself. And I can see as an overlay chart what those three would look like. Obviously, there's a very low risk option, which is selling it now. It means I don't have the capacity for big returns, but I also don't have the, I would then not be exposed to these massive potential losses. I might look at that and say, well, based on the amount of exposure I have here, I want to definitely sell the idea now. Too much exposure. I know that I could make a lot of money, but there are some massive losses there. I'm not willing to take that hit, so I want to do this now. Well, without fudging the numbers, P-Tree will always say the best expected value runs through this path. But I can make an arbitrary business decision based on my own risk exposure, also risk appetite, right-click a branch and force that branch. Forced. Now, the decision indicator knows that my forcing overrides the expected return, and this becomes the best option, true. So that's the force option, and it now means that any reports that I generate are based on what I have forced. But I'll go one more layer of complexity here, and I'm actually going to look into my model and see where are all of those big losses that I had that I didn't like. Well, they were at the end here where I go to manufacture, the product fails, and I have a massive loss. Well, do I actually have to go into production for myself at this point? No. I could choose to sell the idea. If I've proven in a trial that it's pretty good, then someone else can take the limited risk on the product. I'm going to sell them the idea right now. And I could do the same for the contracting as well. So regardless of how I do it, I could force myself to do either I do the testing or someone else does the testing. If the results are good, then we intentionally choose to sell the product. Now, what does that do for us? As you can see, it's eliminated the really high potential outcomes, but it's also eliminated the really bad potential losses. And so I might look at my comparison of my 3 decisions now and say, well, these losses aren't so bad. Clearly, contracting out the initial phases of the program are better than piloting it. So I will take this as my optimal decision. Now that we know we can force the tree to do things, I can go back to my tree and say I will force this branch now. I'll get someone else to do the next phase of testing. If it's successful, then I'll sell the idea. And so I now have as my optimal suggestion this path, which includes 2 forces in it, or 2 forced decisions. Okay, so that's forcing, and it enables you to include risk aversion. Pardon me. Enables me to include the risk aversion in my decision tree modeling. I can, however, formalize that and actually make the calculations in the tree include risk aversion. And I do that using utility. In the model settings for a tree, there's a utility function option. And I can choose to include a utility function. Now, I won't go into the details of how this works mathematically, although it's easy enough to find out, and there is information in our help files as well. But basically, the lower the R value, then the more risk averse I am. So if I put 100 in for my R value, I see that licensing the product now becomes the optimal decision. It has a certainty equivalent, $927. Don't worry about what that actually means, but this, if you like, the value of being here is now better than the value of being in the other 2 main branches because there are no potential losses here. And the big losses that are possible here hurt too much. I'm too averse to those. If I change my utility function R value and make it larger, it means I am less risk averse. Okay, so these values here for the other branches, they're still not as good as the licensing option because there's no downside to licensing it now. But they do have, pardon me, a larger value now. Now, if I bump my utility function up to say 40,000, which is roughly the equivalent of the decision that I would be willing to play a game where it's 50-50 that I would win 40,000 or lose $20,000 in this scale. At that point, that's my tipping point. If the probability of losing or the loss amount is bigger, then I wouldn't play. If it was smaller, then I would play. Now, at that point, I still have as my optimal path licensing now. But something interesting happens if I were to decide to follow the other paths. Maybe strategically the business says it's not worth selling. If I were to contract it to someone else to do the testing, it turns out that the best path is to, if the first phases of the program are successful, then I should sell the idea. However, if I pilot it myself and it's successful, I should manufacture it myself. So the more risk averse or optimal risk averse option with an R value of 40,000, if I decided to pilot it myself, would be to then try and proceed to manufacture. But if I decided to get someone else to do the first phases of the program, it would be to lead toward licensing it out if the product is successful. So some interesting outcomes, but a way in which what I've been able to do here is literally formalize my level of risk aversion. I'll just make it a much bigger number. And now as I've bumped that up to 70,000, I see that in fact, contracting out is the better option. So as that R value gets larger, it becomes more like the expected value decision. So that's PrecisionTree. I'll leave those options there: appending, sensitivities, utility, and forcing decisions. And take a quick look at TopRank. Now, TopRank is a very straightforward product, really useful, just a neat little thing. And for the most part, what people do is simply add some functions, some varying functions to a deterministic model, run the analysis, and get sensitivity results. The basic way that TopRank works is to change your variables one at a time and see how that one at a time comparison compares across different variables. However, what if, pardon me, what if I have multiple variables that could potentially change at the same time? So there are a few different thought processes here. One would be that I'm just interested in knowing about how my output might be changed as different levels of volatility occur in different variables simultaneously. Another might be that I could be interested in including a correlation matrix when I eventually use at risk on this model. Which of my input pairs would have a noticeable effect if they were to be correlated? This is known as a multi-way analysis, where instead of changing variables one at a time, I can choose variables to change more than one at a time. So in pairs, in triplets, and so on. In the analysis settings dialog, I can set my multi-way options. The defaults are the most common, and that is that we have a group size of 2. So in other words, taking pairs of variables that we'll specify shortly, taking pairs and all the pairwise combinations of the variables, alter them as a group, and simply have them in 2 steps. So both at their lowest, both at their highest, one high, low, one low, high. You can do more than that, but that generally gives us the information that we're interested in. So all that's left, in this case I'll go to the model window, is to decide which variables should be included in this. So let's have a look at labor cost. I'll select all of my labor cost variables, right-click, and select multi-way. These now become risk vary multifunctions. The only difference that this has induced is that when we run our analysis, everything still gets varied one at a time as always, but then a second analysis will be run that will vary all 5 of these in pairs. So year 1, year 2, year 2, year 3, year 1, year 3, year 2, year 4, all the combinations as pairs will be varied and the results will be produced. So I'll click OK. Now when I click the Run What If, I can see that there are multi-way recalculations included. I'll select my report settings option and I'll put the results in a new workbook and run the analysis. So the regular TopRank analysis is being run, as we can see here, regular tornado and spider, some information, and now the multi-tornado and the data for it. So where I vary worker 1 cost and, year 1 worker cost and year 5 cost together, or year 4 labor cost and year 5 labor cost, these combinations produce the greatest, in their extremities, effect on the output. So it's all labor costs because they're the ones that I included in the multi-way. Whereas 2 and 3, years 2 and 3, the relationship between those doesn't produce as wide an impact or as great an impact on the value of the total profit. So this is varying 2 of these inputs simultaneously. So my inputs here might be this one goes up 15%, this one goes up 15%, and it reduced my total profit by 172%. All the way down to the bottom, we're changing some of these variables, plus minus 15 netted out at 0, or plus minus 15 with only a 15% change. Okay, so that's a multi-way analysis where I can actually use TopRank to change more than one variable at a time. It's TopRank's equivalent of correlation, basically. TopRank also has other equivalents of at-risk functionalities. Now with at-risk, we can run multiple simulations. And we would run multiple simulations for testing different model assumptions, be they business decisions or states of being in the model, and we would generally use the risk sim table function to do this with. TopRank has its own version that still uses risk sim table, but enables you to run a TopRank analysis under a certain assumption, change the value of that assumption and run another analysis. So exactly like multiple sims runs a simulation per sim, this multiple run feature of TopRank does the same thing. So what I have here is a financial model where I get my MPV for a new product. And currently it's based on there not having a competitor in the market. If I change this cell to a 1, there is a competitor. So my volumes have changed and some of my costs and prices have changed and I get a different MPV. So what I'd like to do is to get results for what happens if I do have a competitor, what happens if I don't, and I just want to be able to do one run or one analysis to get both of those. So a risk sim table function needs to go into this cell. I'll just hard code it for simplicity. but it's the same risk sim table function as at-risk users. In my TopRank analysis settings, I now acknowledge that I have 2 runs to do. It will therefore cycle through a full analysis with this cell set to 0, then update it to 1 and run another analysis. Okay, so there are 2 runs in total. I click run. And I have, pardon me, run 1 of 2, and then run 2 of 2. This first tornado is where the value was 0 on the spreadsheet, which indicates no competitor. And I can see that obviously price and volume were key risks, production costs and OPEX and CAPEX, these were very minimal inputs. When there is a competitor, however, obviously price and volume is still very important, but my production costs, my OPEX and CAPEX become relatively more important. Probably not an unsurprising result. I've got data for each scenario, and I could use that information to perhaps produce even more charts doing the comparison. But I've got tornadoes and spiders for each scenario that I have identified, and those scenarios have been identified with the sim table function. So it's exactly like multiple simulations with at risk, but it's the TopRank version. Okay, I'm going to leave TopRank there, and we'll look at one more example, just one, and this is using Evolver. It's also relevant to Risk Optimizer, but I'll just use the Evolver option. And this is soft constraints. When we constrain a problem, we generally think in terms of hard constraints. Now, sometimes that hard constraint is, like very specifically, it is hard logically. That's it. For example, if I have a portfolio mix problem, the total of my investment is 100% of my investment. That's it. So I need to adjust these values, and the constraint that they sum to 100, that's fixed. They can't add up to 101% or 102. Okay. But in other cases, such as this advertising example, the amount that I spend on advertising, well, I've got a budget for that, 50,000. If I found an amazing decision that needed an extra $1, I shouldn't reject it just because it costs an extra $1. I should actually go ahead and do it and simply find where can I get the extra money from, okay? Now, if you build constraints that are hard, well, any trial that violates the constraint is immediately ignored because you've told the software that's impossible, it's infeasible, don't even think about it. Whilst this is a standard approach to constraints, it also does make it harder for the algorithm to find a good solution. So what the algorithm will do is accidentally go into an infeasible space. That option gets rejected outright, and therefore it essentially ignores the knowledge that it gained by violating the constraint a little bit. So instead, we could allow a constraint violation, pardon me, allow a constraint violation that, pardon me, we don't really want to go over, but if you've got a great idea that does require some extra money or resource, we can probably do it. And also by allowing it to be soft, it means there's no longer any such thing as an infeasible solution. So it gives the algorithms a better chance of finding your optimal decision more quickly because it's not being forced to disregard possible choices or decisions that happen to fall just outside the constraint. So what soft constraints require is a penalty function. How do penalty functions work? Well, we have an example at the top that's not actually an optimization, but it gives you some information about what, pardon me, the different constraints in a soft penalty might look like. In other words, as you violate your constraint, and that's known as the deviation, how much should you punish your the cell that you wish to optimize by? So if we go over by, over budget by $1, how much should we penalize in whatever the units of the output cell are? How much should we penalize that? So we can do things logarithmically, exponentially, linearly, as a power rule, and so on. So this gives us some different information in here about what those penalty functions might look like. If I go to the example file that I've built up, or that I've opened here, I have a budget constraint. It's currently hard. If I make that soft, I need to include a penalty function. And the function will be a function of the deviation. So in other words, as I go over my total cost, like per dollar, how much should I penalize the objective? We will generally include the word deviation in our penalty function. I said that's going to be the unit change here. So I will, pardon me, I'll start with just the straight up deviation. So what's this going to do? Let's quickly check my settings. Okay. So as I go over the budget, it was a bad penalty function because it says you can max out on the number of ads to get your total audience up, and the penalty is worth it. All right, so I'll stop that. Let's go back to the start. So there's a little bit of playing around that can be involved in terms of understanding for your particular needs what sort of penalty is reasonable. So if I look at this and I say, instead of being deviation, it's the say the square of the deviation. So little violations are kind of okay. Much worse violations get much worse, or get penalized a lot worse. So I'm seeing a result now where it looks like the current optimal solution isn't violating the constraint. It shows that with a square rule, the extra cost of buying an additional ad in one of these other categories isn't worth it. In fact, that punishment that gets applied to the objective outweighs the return. Let's go back to the originals, and I'll just do one more example. Instead of just being linear, let's make it a little bit worse, 1.2. So you can see here I've got a solution where if we can, there was 50,800 before. At one point, the current best solution actually violated the constraint by $800. It's since found a better one where any violation of the budget hasn't actually returned a better audience than 149,000. But if we'd stopped it earlier, or maybe the numbers were a little bit different, we may have had a solution that did violate this, which was actually better. Okay, just for fun, the very, very, very last thing I'm going to do is go back to that model. I'll make the punishment only a little bit just a little bit worse than linear, and let's see. Up too bad. So I didn't make it harsh enough. So I'll just try the 1.1. And I'm watching my cell value here and seeing that it's trying numbers bigger than 50,000 now. So previously, 149,000 was my audience optimal value, and I didn't have to spend more than 50,000. If I allow myself to spend $16,800 more, I will actually get to an audience of an extra 50,000 people, which is probably worthwhile. 50,000 people should be worth quite a lot to me. But I only found this solution by allowing violation of the constraint. And this is reasonable. All right, so I'll stop that there and say this is my optimal solution. It does violate the budget, but I'm hoping I can get the extra cash because I'll be able to reach another 50,000 people. Okay, so I'll leave that there. And thank you all for attending and coming along today. As always, this will be recorded and will be up on our YouTube channel, hopefully by the end of the week. That's Palisade Corp. If you do have any questions, please just send them through at any point to your local contact. You can just go through our website or indeed comment on this. If you're watching this live, you can comment here and we'll get your comments and respond to you as soon as we can. Otherwise, hopefully you've got some ideas about how you can use any of those 4 tools in perhaps a slightly different way than you've done in the past, or that you've seen a few features perhaps you haven't seen before. And I wish all of you good luck in your modeling and hopefully see you again soon. Thanks.